levels, and he's a specialist in, among other things, unconventional completions, and he's going to talk to us today about fracking and how to do it properly. Thank you, Martin.
Thank you very much. Good evening, ladies and gentlemen. I'm here this evening to give you a lecture on unconventional gas, but before I start, I'd just like to talk to this first slide, a very important slide of the deck. This is to recognise the Distinguished Lecturer Programme, funded by the SPE and various other organisations, including offshore Europe, Amy. It's a very worthwhile piece of business that the SPE supports. Gets information out into the SPE sections around the world, various places, very diverse. It's well funded now and is well supported, and as indicated, like I said, up to 30-35 lecturers this year. So an expanded programme. Please do keep the support to the SPE, and all of the lectures are typically downloadable from the web, the SPE homepage. There's also, I'll get to at the end as well, the review, the feedback slide, and I encourage you all to go and provide some feedback. I'm going to talk about hydraulic fracturing, and as you're all aware, I don't suppose anybody in this room hasn't heard of hydraulic fracturing. I've been in hydraulic fracturing for some 28 years, but working with hydraulic fracturing, but very, very popular for all sorts of reasons around the world. So I'll start with the first slide. Whenever I move into a country to give a lecture, visit, I always check the local newspapers out to see what's being talked about fracking. Invariably there is. I didn't have a chance to look in London today, but I did look in Aberdeen last week before I gave my lecture. I just want to show this slide. This is from the Aberdeen Press and Journal, Denny Frack. And just want to demonstrate that there's clearly an education gap between the general public and fracturing, not least around spelling, because as we all know, the only K in frac is permeability. So please encourage you with all of your various societies, companies and organisations to spell fracking as hydraulic fracturing or fracking with 2 C's, because that's the way the industry refers to it. Okay, so far from that side, we'll press on. So I'm going to talk about unconventional completions, paradigm shift, a game changer for shale gas, tight oil. Lots of words kept getting added there. People wanted to expand on what it was about. But really, I want to describe to you the process that we follow to obtain these unconventional resources. And I think as you'll see what that process looks like and how we unlock or crack shales, if you'll excuse the term, we crack them in a certain way. It's probably not the most efficient way, and as an industry now we're starting to rethink some of the approaches that we're applying. And I'll just cover a little of this tonight, and you'll see that there are some people in the business who are starting to revisit some of the basics and see what the additional opportunity will be. There may be a few surprises in here for you, especially for those who have been involved in conventional oil and gas for most of their careers, as this is very different. So, if there's anything that we could refer to as a typical unconventional frac design, it's going to look something like this. It's going to consist of an awful lot of horsepower on location, a lot of very big pumps, 30 to 50,000 horsepower rigged up on location. That's an awful lot of pumping capability, and the treatments are pumped at anywhere between 80 and 120 barrels a minute, which is a very, very high rate. You can work out what that is in barrels per day. It's a very, very high rate, and I'll explain a little bit about that in a moment. Wellhead treating pressures can be anywhere between 10, 12, 13, 14,000 psi, and one of the effects of pumping at very high rates, at very high pressures, is that equipment deteriorates and requires a lot of maintenance or entire replacement very much more rapidly, because working up at the top end of the envelope, the pressure envelope, has a much more serious impact on erosion and capability of the pump through its torque and the fluid ends. Fluid volumes are very large as well, up to 1 million gallons on what I'll refer to as a stage. We perform several stages within a well, but a single stage typically consists of about 1 million gallons of fluid. And in unconventionals, on the whole, this is slip water with perhaps some viscosity applied during what we call the slurry stages, when we're adding some of the sand. So that brings me to the sand, or what we call proppant sand. Large volumes of proppant, 200,000, 300,000, 400,000 pounds of proppant per stage. I think the market for sand now internationally runs at about 18 billion pounds of sand annually. So a very, very large volume of natural sand, which in itself, because it's very angular, is very erosive. Unlike some of the man-made proppants, which are more spherical, have a higher roundness, tend to be less erosive than the sand itself, but more expensive because they are manufactured materials. So the key here is we're trying to pump at 80 to 120 barrels a minute. And why are we trying to pump at such a high rate? What's the driver to pump at that high rate? Well, when we started to work in unconventionals, we didn't have a lot of downhole jewellery, lower completion tools to make selections as to where we were fracturing. There were very, very few tools available. On the whole, it was cased and cemented liner through the reservoir, which we then added perforations to create access to the reservoir. So rather than trying to initiate a frac in multiple stages, 60, 80, 100, we couldn't afford to do that. So we tried to fool nature. We perforate in 3, 4 or 5 places, we create connectivity with the reservoir, then we pump at 100 barrels a minute at surface, with the intention of 20 barrels a minute going into the first set of holes, 20 barrels a minute into the second set, 20 into the third, and you see where this goes. But for those of us who've worked in the oil industry and worked with rate diversion, as we call it, it didn't work very well in vertical wells when we tried to do it, and certainly why we thought it would work well in horizontals is a little bit beyond us. But that's what we try to do. We're trying to fool nature, which never really works well. We're trying to play poker with nature and put 100 barrels a minute through 5 sets of holes in the reservoir. Now, Mother Nature doesn't like playing poker, generally wins, it's a slide player, and picks low energy solutions. And so what we often see when we run a PLT, either on injection or on production, is that out of those 3, 4 or 5 perforations, only 50% are actually contributing. So we've only broken down about half of those. So the industry's approach has been not to run PLTs because they cost money. So we don't want to see the data that tells us that we're not doing what we plan to do. So we just play around with these clusters, each one of these being referred to as a cluster, and continue to pump at high rate. So we're trying to put all of these fracs through at the same point in time, and all of the evidence that we gather, or most of the evidence that we gather, suggests from PLTs, from seismic, that that's actually not being achieved very well. So an interesting approach. What we're trying to do, well, this is what a typical frac would look like, typical location would look like. Very large location, this one in Canada. A lot of pump equipment, in this case a lot of vertical tanks storing fluid, but a massive piece of earthworks in order to get this in place. And what we'll talk about then is what are we doing, which we've said, there's these high-rate water-fracs. Why are we doing this? What would ideal look like? How could we achieve that? And what would be the benefits if we could achieve ideal? If you consider the importance of rock fabric, what are we trying to do? If you consider conventional hydraulic fracturing, most people will be familiar with conventional hydraulic fracturing that we performed for 50, 60 years as an industry. And it's where we create a plane, a single frac within the reservoir that responds to Darcy behaviour when we draw down. And the gas or the hydrocarbon moves towards the frac. We create a superhighway within the reservoir. And if we were to take a sheet of an analogous situation of natural glass that's formed naturally and has got a stress state associated with that forming, where the minimum stress is in this direction, and we hit it with a ball peen hammer, we get a dominant fracture behaviour. There's some nonsense going on immediately where we hit it, but there's a dominant plane. There's a preferred plane to the direction of the frac, and one fracture becomes dominant. So in conventional hydraulic fracturing that we've been performing in oil and gas for 50, 60 years, this is what it is that we're trying to create. This is the situation that we're trying to create. Very successful. As we've moved on to unconventionals, this is what we're trying to create, which is dendritic. It's what we refer to as dendritic fracturing. So in this particular analogous state, I've taken tempered glass, safety glass, that's been formed with the specific purpose of having a uniform stress state. And when you hit that with a ball peen hammer, you create this nest of fractures. So in a conventional reservoir, if we were to create this due to the stress state and perhaps the rock fabric behavior, if we had a vertical well at this location with a certain radius and a certain reservoir thickness, there might be a surface area of 1 exposed to the reservoir. From a fracture, a planar fracture, we can increase that 1,000-fold. We can create 1,000 times more surface area exposed to the reservoir, which is why hydraulic fracturing in conventionals is extremely successful, extremely robust, and has typically very good results. In a nanodarcy reservoir, if you were to create 1,000 times more surface area, you wouldn't flow the well. You may get a small amount of gas, and that would be a very quick transient and no other behavior. What we're trying to do is create 100 to 500,000 times the surface area out of a single frac compared to a vertical well through the reservoir. Because these cracks are dendritic and are in a 3D space, a cloud, we're actually accessing the gas molecules. The gas cannot migrate through nanodarcy. The Darcy's law is all very useful for conventional reservoirs, but when you get down into nanodarcy, gas molecules are not going to migrate towards this frac through the matrix. The matrix has less permeability than the cement that we're isolating the well with. What we have to do is we have to physically create what's sometimes referred to, although losing popularity now, a stimulated reservoir volume. We have to hydraulically actuate the reservoir. We have to physically create, if you like, the reservoir by using the rock fabric. It might be microfracturing within the shale. Shales are very laminated as well, typically. There might be some blocky tendency. There might be a stress regime that's fairly uniform. Again, God's been very, very kind to fracturing in the stress state that keeps vertical fractures within the reservoirs, within conventional reservoirs. But he's also been very kind in the fact that the stress state is very, very uniform in the lower 48. So if you look at a world tectonic map, plenty of places on the web, you can look this up, and you see where the world's tectonics are, what the current situation is, where continents are on the move, where we're getting plate tectonics, uplift, etc. There's a lot of tectonic activity around the world, apart from in the lower 48. It's a very passive basin on the whole. There are some structural impacts on the stress states, obviously, but on the whole, there are large swathes of Texas, Oklahoma, and other states that have got very, very low differentials in stress in the shales themselves, a few tens of PSI, which lends itself to Mother Nature changing direction or wanting to create dendritic behavior. If you have a dominant stress behavior, nature wants to create, just work against the easiest path and create a low energy solution. So what are the properties of unstressed or equally stressed shales is that it will help you get this, rock fabric will help you get this. And also, of course, shales are somewhat more malleable, have a lower modulus, Young's modulus, than sands, and so over the millennia, these shales have not tectonically been on the move. These stresses have also had a tendency to equalize somewhat. So shales lend themselves to this in the right location. There are plenty of locations in the world where there may be shales with lots of resource in place, because resources typically not the problem. It's not like typical conventional. You're not going to prove that the resource is there. It's often known to be there. From all the drilling, conventional drilling that's gone on over the years, and the mud logging and the gas that's been seen in the shales. It's whether you can create this when you frack, or whether you can create this. This is certainly one of the effects that potentially causes sweet spots, which you often hear referred to. So if you can get this surface area increase, then you're well on the way to having effective unconventional agriculture. So, cluster efficiency, each stage within a well should look like this. We want to work from 3, 4, or 5 clusters of perforation. This is the well wall. We have 3, 4, or 5 access points into the reservoir. And we want to effectively drain, create this dendritic, this cloud of behavior within the reservoir. So it's much, much more akin to mining than it is to conventional reservoir engineering. And that's something that people struggle to transition from conventional petroleum engineering to unconventional. As you get down, frac engineers always talk about extremes, so I'm talking about the extreme low cases. As you move towards nanodarcy, it's far more comparable to strip mining. We're trying to mine the gas from the location, from each location, and mine that material out. If we don't hydraulically actuate or initiate at that cluster location, we don't get the gas here. We can come back here and check the pore pressure 5, 10, 15 years later. This is drained, this is a virgin pore pressure. The gas molecules haven't moved. There's been no flow regime, no graduation of the gas from here to these mined areas. So this is a lack of efficiency in the placement of the hydraulic actuation results in a lack of resource recovery, lack of reserves. This is a video I'm just going to play. I'll start it off in just a moment. What it shows is a scale drawing, 100 meter blocks of 3 wells drilled in a lease called Gates. You can see how close the wells are together. Each of these coloured stages is a stage that's going to be placed through 4 clusters. These are treatments being placed over, it looks like 2.5 days. And what we're looking at is microseismic activity. So a plan view from above, the drilling pattern is here, we've drilled these 3 horizontal wells. We've got a surface buried array, and we're listening to the shear events. This is the important point to know about microseismic. Microseismic is not listening to the rock cracking. Those are tensile events. They're an order of magnitude smaller, those packets of energy at least, than the shear events. But what we can do is we can hear the effect, the shadow of the frac. The shear events have a larger impact, and so as the pore pressure increases and you get some shear fracturing occurring, we can hear that at surface and we can place these events. And as we can see, a little bit of a break here and then on to the next cluster. So this is an interesting experiment that we were performing to see if we can improve that efficiency from stage to stage, not by reducing the number of clusters, but by doing something that the industry's done for a long time in verticals, which is called ball drop, which is you get treatment about halfway pumped, we go back to a very clean fluid, stop the sand, keep on pumping, we then drop balls, bio balls that will degrade on flowback when the hydrocarbon comes into the well. And what we see, the orange signatures, are the second half of each one of these stages when the balls are seated and they're creating more volume, more stimulated reservoir volume. So we're starting to get to the point where we're playing snap with nature rather than poker, and we're improving the odds, if you like, of breaking down these individual clusters and trying to improve the overall coverage. This is a side view, shows the top of the reservoir, the bottom of the reservoir. About here, we're getting fairly good confinement, and we're getting fairly good coverage. In fact, it looks like we're hitting this offset well, which will be being monitored all the time that we're fracking, and see if we get a frac hit. It's when the fluid or the frac from one well reaches another. But you can see from a reservoir perspective that this is a mining business at this end of the scale, at this end of Darcy's law, if you like. This is all about mining gas. So mining equations and mining efficiency is much more important than conventional reservoir engineering. And in terms of the placement themselves of these clusters, some companies spend a lot of money running logs and trying to determine where there may be a brittleness factor associated with the shale. You can improve the amount of dendritic behavior that you get. Some companies use a perspex ruler and decide how many stages they're going to pump, and then they use the perspex ruler to determine how far apart those are going to be. Simple calculation. So it's a petrophysicist in one company and a perspex ruler in another. So geometrical placement is just as popular in the industry as conventional petrophysics. Again, important that we, as an industry, we're still learning what are the important subject areas that we should be transporting wholly or in some amended form from conventional petroleum engineering over into unconventional. So another interesting point, looking at the Eagle Ford here, Haynesville, and perhaps less so the Bakken, which is a little bit more permeable. But over the years, the number of stages has increased. So we're constantly increasing the number of stages. Some plays, some parts of plays may have an optimum number of stages associated with them, but an almost doubling of stages in the Eagle Ford. Similarly in the Haynesville, up to 20 stages typically on a well in 2011, and almost doubling again in the Bakken. And so it's this constant increase in the number of stages and reduction to some extent in the number of clusters, demonstrating that this is a mining process, not necessarily conventional petroleum engineering. Important point to note that during 2012, there were about 2,000 wells in the US at the end of 2012 that were waiting to be hydraulically fracked at the end of the year. 2013, at the end of Q2, that had grown to 2,500 wells, and we expect that by the end of this year, there will be 3,000 wells in North America waiting to be fracked stimulated. So this factory that's building these things continues to roll, continues to get much more efficient, continues to create longer and longer laterals, although a big driver for the lateral length is actually not the drilling limitation or the efficiency. More often than not, it's the lease plot size. You can only drill to your border, you can't drill into your neighbour's plot. So that's certainly a limit in the Bakken, where 10,000-foot laterals are drilled regularly, and typically in the Eagle Ford as well, where it's much smaller, 5,500-foot laterals. So how do we support this monster? How do we keep this work moving forward? Well, there's a plot that's quite astonishing if you think about it. In 10 years, we've moved from about 2 million horsepower available in the lower 48, working in the oil patch, to about 18.5 million horsepower currently working because of these supersized fleets. So it's a massive increase in the amount of horsepower. And you don't just build this and it lasts forever. When you're running it at 10, 12,000 psi and you're running it all day, every day, and you're having to occasionally shut it down to let it cool down before it does its 1 week's work on a location, several wells, and moves as opposed to the next. You have to replace this horsepower regularly. There's a depreciation associated with it and maintenance. But it's being driven by the horizontal well count, which is now at 18,000 wells a year in North America and continuously climbing. We had a brief hiatus, I guess 2-3 years ago, took a breather as people moved from dry gas to wet gas, because one of the side effects of unconventional gas is that we've almost made dry gas a distressed product in North America. We've never the other way. So gas prices collapsed. We're moving to liquids to try and generate value out of liquids as a business, as an industry, and gas becomes ever cheaper. Gas export looming on the horizon. Not sure what effect that will have on the UK's gas price, not much, I suspect, after all of the transport and liquefaction and deliquefaction, but certainly a very impressive conveyor that continues to increase. How far it will go, the Bakken is close to 900,000 barrels a day. It will approach 1 million probably before the end of the year, and the game goes on and on. But how supporting this is very difficult. So the number of crews have dramatically increased in 10 years. The competence of those crews, the equipment capability. It's important that we ensure but we still have the same competencies and the same capabilities. But this is the engine that's driving all of this, and the behaviours in terms of large factories. So, if you look at a summary, we drilled these gas wells from these very, very large pads, these large locations, because we want to put a large solution out on that location. That's what typically the pads for wells at these depths, 8 to 10,000 feet, were not that large, really, quite small footprints. But as we've added this requirement for a huge stimulation fleet and pits or tanks, whatever format we decide to use to deploy the fluids themselves, then we've had to dramatically increase that surface footprint. We of course drilled multiple wells from single pads because we have such close spacing. It does lend us that release. We also have quite large diameter tubing and casing. Most of these jobs pump down casing. And with high burst ratings, because these are all in support of 100, 120 barrels a minute, and 10, 12,000, perhaps 14,000 psi wellhead treating pressures. With associated friction, of course, using a lot of energy in friction. Our clusters are down here, and we've got things like a 15k tree on top of the well that we're able to pump through, as well as flow back through. So the well is very much in support of the stimulation technique that's been adopted. So we have an increasing number of stages per well, and we ask ourselves then, so why are those stage numbers increasing? And it's because it's hydraulic action that enables the flow. If we do not hydraulically actuate the reservoir, we do not hydraulically enable it, we do not get gas production. The gas remains in place. The resource is there, but we must hydraulically motivate that gas to produce. The scarcity, lack of availability of horsepower, so everybody's always waiting on horsepower. Even though we're constantly building more and the backlog is getting larger in terms of providing it. And why do we need to use so much hydraulic horsepower? Well, because we want to pump at high rate. It's a self-determining solution. We need all of that horsepower to be able to do all that high rate, to be able to treat those multiple clusters. The drilling completion workover costs that we have associated with the industry, so why are the wells built the way that they are? Why do they look the way that they do? Because the wells must also enable those high rate fracs. So everything about this business is stimulation, is solution related, as opposed to in conventional, where more typically it's got something to do with the reservoir. So a harsh summary perhaps of unconventionals, that we build pads, drill case, complete wells, in order to deliver a stimulation process, which is approaching the physical edge of its limitations. So this equipment is in high demand, it works a lot, we keep building it, replacing it, the number of fleets constantly increases, and the backlog is growing along with it. So we're pumping up at high pressures, pumping lots of solids through these pumps. They last a shorter time period than if you're pumping at lower pressures. It's that simple. Reservoir considerations are almost secondary, and we do not even deliver what we design. What do I mean by that last point, when we don't deliver what we designed this whole monster beast for? Well, we know that we've got 50% coverage, because whenever we log a well, we only see half of those clusters producing, typically. On average, obviously, different plays have different behaviours, but about 50% of clusters produce in your average conventional play. And one-third economic, what do I mean by one-third economic? Well, of course, it's quite a complex story. It's related to gas price, but very typically, a rule of thumb that's used in North America when people enter plays at a certain gas price, and they're costed on that, is that a third of the wells that I drill will make no money, they will lose money. A third of the wells will pay for themselves and break even, or pay out their construction costs. And a third of the wells will pay for the program and be a reason to be in business. So it's very, very different from conventional. You can't imagine going offshore to a 30-slot platform and saying that these 10 slots are going to make me money and the other 20 are just going to be part of the statistical distribution that I have in the field. So it's mining and it's a statistical play, and those really are two things that are very, very important to bear in mind So, it was a harsh summary, wasn't it? There's the project timeline. We're probably all very familiar with various forms of this. Well, we have time, schedule, cost, resource, scope, quality of time, cost, and scope. Time, cost, and quality. Also known as quick, cheap, and good. Yeah, tongue in cheek. So quick, cheap, and good. But this is the way that North America cracked shales, was with fast and cheap. That was the solution. It took a long time. People refer to the Barnett, where this really started, as the 30-year overnight success. It did take a long time to get the combination right, but fast and cheap is really the part of the project triangle. So any two of these you can have. These are the two that North America chose to develop unconventionals, to have the first crack at an unconventional business. The machine at surface needs to be in, it needs to do everything very, very quickly, and it needs to get out and go on to the next one. There's no surveillance, really, not a lot of surveillance, not a lot of diagnostics going on, a lot of individual design that we do in conventional, not a lot of money being spent on time, because we need to be off and move on to the next one. Statistically, it will play out and pay out over time. Depends how that distribution is. So, again, important that we understand that these are the drivers currently in North America, not to say that that's not changing. So what's the missing link? How do we breach the gap and move forward? It's a bit Darwinian in a way. You know, we've arrived at this solution through some early selection because options were not available to us as an industry. But since we started to develop, certainly in the last 2 years, there's been a plethora of new completion equipment arrive on the scene. It's given a lot more choice and selection capability to the engineer, and we can actually start thinking about optimizing some of that mining. So the phrase that's often referred to is that to achieve this ideal solution, what we really need is a lower completion that has open hole efficiency. And what I mean by open hole efficiency is most open hole systems that is not cemented in within the reservoir utilize something like a ball drop. So a ball is dropped to the surface to actuate and move you on to the next point of access to the reservoir. So you don't physically have to enter the well with coiled tubing or a wire line. Some time-consuming and costly exercise is literally just walk over to the well, put a ball in the top, pump it down. It moves you on to the next location, and you're comfortable. But there have been issues with that because you're not entirely sure where that ball will seat. There may be debris in the well. What we always said when we were in verticals is we know everything that there is about hydraulic fracturing, apart from the length, the height, and the width. Like everything else we've got nailed down. Now in horizontals, it's where we are. With ball drop, it's very difficult to know where you are on that said axis. So what we really want is this open hole ball drop efficiency or some form of actuation that's remote, but combined with cased hole accuracy. What we like about working in cased and cemented hole is that we pump the plug down, we set the plug, that's our reference point, we shoot our clusters, we pump the frac, we come out, we then go back in with wire line again, pump it down, and so we have a physical reference point. So we want to combine, you'll see a lot of churches. Of course, a lot of those churches are Kenai Drilling and other drilling companies drilling away merrily. And treatment optimization, well, how about this? We could actually start to design the treatments, each one. We could use water from a flowback well. So we drill multiple wells from a pad, but we go in very quickly. We pump all the water into the wells, and then we start to flow back all the wells together. Well, water's a very, very sensitive issue in the US as well, particularly anywhere with fracking, because fracturing is seen as consumptive. Even though it's less than 0.1% of the water utilised in the US is associated with fracturing, it is seen as consumptive, and so we're actively looking at ways of processing that water and reutilising it. So if you were on a location for a longer period, and you were taking flow back from well 1 and you were working on well 2, we'd be separating the gas and the water here, using the gas probably for power generation rather than diesel for these pumps, and then putting the water back over into these tanks, with some being delivered, of course, to the location. Let's say you get 20% of your water from your flowback well when you're on well 2. When you're on well 3, maybe you've got 50% water coming from the flowback wells. By the time you get to well 6 or 7, maybe 100% of the water you require is coming from the wells that you've already treated. And certainly separation's coming because the EPA in the US have mandated what we call green completions and some emissions laws that means that we will not be flaring gas to the extent that we are now on cleanup, and we're going to have to reutilize it. So what better way than utilize it when you need it for power, and put turbines on location, electrify these pumps, which has been done, or is certainly being considered being done. There is certainly LNG, there is dual fuel systems now for pumps that run on gas and diesel, but we haven't gone the whole way yet with full gas. But the option remains. We can improve the frac spacing. We can do bespoke stage frac design. Let's say that our petrophysicist is not a perspex ruler anymore, and let's say that we can change the design of the stage a little bit from one piece of the rock to the next. Less fluid required here, more fluid required there, because we're actually learning something. Perhaps we have some kind of selection process, frac or not frac. If we see a certain tank response to a short injection, a breakdown, we say this is not a place we would like to frac, because we can tie that back to responses where we've seen low kerogen maturity or low frac delivery from PLTs that we might run to actually gather some information. So that we cycle that information around and make the improvements. Production optimization, well, delayed workover because we don't have to come back to this well within a month and put a smaller tubing string in it, because the casing size is organised and arranged and selected for the reservoir in the first place, not for the stimulation solution. We get an improved well IP due to that stimulated reservoir volume. So we know that we're touching more gas if we're improving that access point, so we must improve the initial production, the IP of the well. And improved well hydraulics, so with smaller casing, smaller tubing, we keep the well flowing longer before we have to intervene and do some form of artificial lift or sweep to get liquids out of the wellbore. And maximise the recovery per well. The interesting thing to note is a lot of operators working in these plays, the Haynesville, Woodford, all of their dry gas, other plays including the Eagle Ford, which is wet in places, do appreciate and acknowledge that they'll probably have to go back and twin these wells at some stage to access that resource that lies untouched. We're currently, within our own company, refracking wells that were fracked 3, 4 or 5 years ago with some success, because we're managing to divert to those pieces of rock that are unstimulated. But if we could get it right the first time, there would of course be no reason to drill as many wells or ever to go back and drill the same number, depending on how your economics work. So will take longer, of course, to do it this way. How much? Well, not as much as you'd think. Estimates look at perhaps 2, maybe 3 times as long to treat the pad with this smaller, what we call slow frac, which is being adopted in some places. And there'll be increased costs. How much? Big question mark, because most of the contracts in North America are built around horsepower that you utilise. Now, you take the horsepower off location, those contracts don't work very well anymore. So the service sector is going to have to determine something. Is the best cost model? If you look at that 18.5 million horsepower, that's 750 frac fleets in North America. So if we broke it down to say 8,000, 10,000 horsepower, that would be 3,000 frac fleets in North America. So there wouldn't be much of a backlog. They'd be moving around slower, but they'd still be getting the work done quicker, even if they took twice as long. So what might some of those benefits look like? Let's say, in terms of the area pad, at least a 50% reduction. At least a 50% reduction. And the social impact of that, of course, is that there's less disturbance. When we've had oil field, we've had unconventionals in a number of places for some time, but when we started to impinge on cities and populated areas, it's fine to go up to West Texas and do this, or Oklahoma, but you start to do this on the edge of New York, and you're getting people's attention. Or up in Pennsylvania, where they haven't had oil field for nearly 100 years, it starts to impact people. So smaller footprints, Production rates, well, we should get maybe 50%. Let's not say we double it. Let's just get a 50% improvement. We move up to 75% of that resource being touched. Efficiency on the number of wells, well, less wells and certainly less refracting and redrilling. The casing weights will all come down, the casing sizes will all come down, the drillers can optimise their business. As we always did in the oil field, they can optimise their business, the reservoir will optimise its piece, fracturing will have to like it and lump it. Process and cleanup, we utilise that gas. Well, utilising the gas gives us the water on separation, so we optimise the reuse of that water, which with slick water is not too difficult a thing to do, depending upon the constituents. But the reuse of the gas on flowback, it's coming anyway through the EPA on emissions laws. So there have already been a number of initiatives called green completions in the industry. People are moving towards that and reutilising that flare gas. And if you can utilise that flare gas for power, there are at least 2 companies that I'm aware of that are looking at taking the motors out of the big diesel electric trains and putting those motors onto locations and using turbines with gas to have an electric frac fleet and plug and play. You wouldn't have to build a lot of it. Those pumps are dial-up rather than gears as well, so very, very efficient. And of course, these pumps last a lot longer now because you're operating them at 6,000 or 7,000 psi wellhead at lower rates as well. You're only pumping 20, 30 barrels a minute. So these fluid ends and the torque through from the motor all makes the entire piece, the investment, which is a huge investment, last longer. So keeping up with that 18.5 million horsepower and climbing curve becomes less of a problem. The completion, our workover, so less workover required, so we don't have to come back to the well as often, which is not only good for us in terms of cost, but also good for our neighbours and the people that live in the region, not having workover rigs and crews coming through the gate on a regular basis to spend time on the wells or the path. The completion itself will probably break even because you're going to spend more money now on the lower completion, on some of those tools that are available and allow you to select these approaches. Putting on production, although it's taking longer to treat these wells because we're moving the backlog, we actually get them on production at about the same time. So it's a break even. And the frac stim costs themselves, difficult to say, but there'll be some increase associated with individual treatments and that extra time, personnel, and investment. How much that would be somewhat open to debate until we start to do this. I guess one of the interesting things about this is being in London and talking about this. This will be slow. Parts of this are starting to happen in North America, but it will be slow to really turn over to this because there's an ingrained business model that people are very reluctant to move away from. But if you look at international exploration and development, this is something that has a much more appealing look to it for populated areas, for sure. It also means that you don't need to have 50,000 horsepower lying on contract, not doing anything for a long time, until you need it for a couple of days and relying on contract again. So your ability to use a lot less horsepower to see more of the value out of a single well, I think lends itself well to exploration and appraisal, not only in populated countries, but remote areas where such horsepower really doesn't exist. So the goal, if you like, is to drill and complete fewer wells with better initial production and more reserves per well, or just more wells, and liquefy it and ship it overseas. If we look at some of those intangibles and talk them, there's this lower impact piece. Socially, we have a lower impact. If you go to the Bakken in North Dakota, you'll see a lot of issues with the impact that the oil field has had on the Bakken, because when we go in as a business into a town and we develop a piece of the Bakken, a school teacher can leave work and haul water for us for a company and double his annual wage. So that's a bad impact socially. Mom and pop who go down to the diner on a Friday morning for their weekly burger not only can't get a seat because it's full of roughnecks, but the price has trebled because the oil field's in town having a burger that day. So there's a lot of social impact that we need to consider. Less lower hydraulic horsepower, it's just less noise, and this might be, it might sound odd, but excuse the pun, but it might sound odd, but there actually is a big impact. These locations make a lot of noise, and if they're hammering away for a week, on a pad, or 2 weeks on multiple wells, that can have a detrimental effect. If you're working the pumps at lower pressures, and you're working less of the pumps, and you perhaps have them enclosed in something that looks like part of the community, then there's certainly less noise impact. Less water because we're reutilising, and water will become a bigger and bigger and bigger issue over time. We're always looking for ways to use to be less impactful on water utilisation. I suspect that in the long term in the US it will go something towards water trading, like carbon trading, and that businesses that can demonstrate that they're impacting the volume on an annual basis, and they're using distressed water from power plants or from some manufacturing process, are going to be able to want credit for that, and you can see a credit system operating in that way. Lower pressures, fewer wells, less workover. Cottage industry. People talk about frac factories in North America. We've got to start thinking about frac factories. It doesn't go down well. But we've got to start thinking about cottage industry. Let's do the same business in a more efficient manner, less impactfully, but we do 4 times as much of that. We can split that horsepower up and make at least 3 times, 4 times as many work fronts. So more detailed work rather than the factory. The goal, as we indicated, drill complete fewer wells with better IP and more reserves per well, and less disturbance to the environment, and that's socially the community. Build with the community, don't fracture the community relationship with the community, but actually build a decent relationship. And this is one of the approaches we believe will have that. So in summary, the industry's been developing and accelerating these new lower completion concepts onto the market. These tools, when combined together, can give you that holy grail of open hole efficiency with case hole accuracy. It potentially allows the industry to reassess various aspects. So almost all the aspects of well construction and our business can be reassessed in light of doing things differently at the actual stimulation solution. So more thoughtful and more efficient around the well construction process, the land access, the completion, utilization of materials, flaring, etc. It's the trigger to re-examine all of those requirements. The result could be a doubling of reserves, improvement in recovery factor, and improving that economic well ratio. We're starting up from 1 in 3 to, what could we go, 50-50, maybe even 2 in 3 would be economic as a starting point. Very important, such an approach can directly improve the relationship that you establish with the local community. A lot of the spin-offs from these considerations have direct beneficial impacts on being in and around large communities. And that shouldn't be overlooked. It's less tangible, absolutely. But in the long run, that relationship is very, very important. Again, I'll quote Sam Wang in Colorado. My own company's been in there for close to 40 years with unconventional development, and it is part and parcel of the community. Really determine where the community ends and the oil field begins, because of that very, very long road to building that relationship. So it is part of the business. You'll hear a lot of people talk about sweet spots in unconventionals. That might be related to the rock fabric, that might be related to carriage and maturity, might be related to stress state, structural issues, etc., etc. But I can guarantee that one of the sweet spots in unconventionals is right there. And it's getting the balance between quick, cheap, and good. Absolutely correct. Okay, with that, I'll move on to feedback and just request that you do provide some feedback you get the opportunity, it is important. It is ready to take any questions.
It seems in simple terms, you're basically saying fraction one stage at a time, and you need less power.
Absolutely, yes.
And that's just not done at all.
Not really, because when we started, we didn't have the tool selection choices. So if we wanted to treat 3,000 foot lateral, when we started this whole unconventional approach off, our real choice was plug and perf, really, at that point, which is where we pump the plug down. Now we can afford to do that $50,000 to $75,000, $100,000 operation about 10 times, about $1 million. And so there's still a lot of rock there, so it's create clusters, pump at a really high rate and try and split that flow up. What I'm saying now is that there have been a lot more tool development that allows us to move very rapidly from one stage to the next, to do, rather than 10, to do 40 bespoke fractures. And of course we don't need the same rate now because each one is being treated at the rate that's optimum. And I just want to say something about the optimum rate. Mike Meyerhofer wrote a paper a couple of years back that demonstrated quite clearly that no matter what your cluster selection was, once you got to about 25 barrels a minute in certain parts of the Barnett Play, your machine, as a statistical cloud, stopped moving to better IPs. So plays have optimum rates. They're not as high as you think they are, which Mike demonstrated. And we don't have simulators that really validly represent what's going on in the formation. So when we pump at these very high rates, we lose a lot of energy in friction. We have poroelastic effects, increasing pore pressures in the formation, which drive less fracture width, which cause more friction, which take more energy out of the system. So it's not really surprising that there's an optimum rate associated with a fracture in a particular play with certain parameters. I'm not saying it's always 25 barrels a minute, sometimes it may be 30, sometimes it may be 10. But it's not really that surprising if that's the case.
Neil Randolph, and I was very interested by, you described a lot of technology, not a lot of science. It's like 50 years before you break it forward. How long do you think it be before we can apply science rather than technological understanding, experiential learning?
Very good question. There's lots of research going on. There's not a lot of great surveillance on that. It reminds me very much, if you've been involved in fracking, you'll noted the period in the late 70s, the early 80s, where the rush for tight gas, Darcy behaviour gas, fracking out of vertical wells, massive hydraulic fracturing, got a boost from the Gas Research Institute in the US, and there was a tariff on all gas produced, a cent, that was placed into that and funded universities and research centres for many years, and was really the push that fracturing needed to get conventionals to the very simplistic approaches and well understood approaches that we have. I feel personally that we need something similar to that again to get unconventionals, fund universities, fund research centres have centrally coordinated technical innovation to just push the industry. We don't have simulators to represent this dendritic behaviour. If there are simulators, and there are some that are being used or adapted, interestingly enough, they're from the mining industry, the jointed rock codes and such like. So it kind of backs up the fact that this is much more related to mining.
Do you see Brazilian never even brought in the United States?
We'll see.
My name is Artifact from RWE. My question is very specific about the software that you probably recommend based on your experience, if you can recommend at this time, and also how completion engineer communicates with the reservoir engineer in such complex situation. How do you see the industry, in this industry, who should do it in your view as the end user of this design process?
Okay, so software is a difficult area because the software really doesn't exist. There are a number of companies that, I don't want to mention products and companies, but there are companies within the oil field developing software, have packages available that they believe to some extent represents the dendritic behavior. Knowing that dendritic behavior is taking place is not matter and what's driving it. There are other codes from the mining industry that are being adapted by various consultancies to try and work in this area as well. In terms of the completion aspects, what is the real driver for the innovation that's starting to happen now are the small companies, the small startups that see this problem and go away to the lathes and the tool sheds and build solutions, and then inevitably bring them into the industry through pilots, either I'd like to see funded pilots by some central organisation or by individual companies, because they know a man who knows a man, but eventually get snapped up by the majors on the service side and go into mass production. Because sleeves, in terms of sleeves, the industry produces, I think it's 6,000 sleeves a month. So it's a massive manufacturing. You come up with a new concept, it can get tested very quickly, but then you've got to retool to build it in a very insufficient quantities that can keep up with the requirements. So it's a very dynamic situation, but it's moving in the right direction. More stages, less clusters, less trying to play poker with Mother Nature, and more snap. Moving the odds in our favor. Sorry, I'm not very good at this. Yes.
Just to be clear about this culture approach of technology service. Are you saying that the shale gas fractures are routinely being designed using the same models as were used in the 1980s for mining fractures? In which case, how on earth are they able to simulate accurately a design to work?
They don't, but then what happens is people design statistically. You not only look at the behaviour of your own wells, where you perhaps change the volume, or you change a volume of proppant or a volume of fluid or a rate, but you look across the fence at what your neighbours do, because all of this, and of course in North America, is public information. It's all loaded onto.
So can I just elaborate on that? I mean,
Yeah.
we've been told here in the United Kingdom that all this wonderful technology is coming over from the United States, all scientifically, and it's going to solve all our shale gas problems in the UK. What do you say?
I'd say that we're accessing 50% of the potential of the wells in the US now on average, and I'd like to see that increasing to 75 or 80%. But the models, there are research codes to try and generate that dendritic behavior. Of course, highly complex. Even with today's computers, when you're working in 3D, the computing time goes dramatically through the roof. So rules of thumb are the average way that people benefit, and people look at IP trends, people look at what other companies are booking as their volumes per frac, stage volumes of proppant, and if they see that their IPs are getting better in a play, and they see that that's due to the fact that the volumes are increasing, then they do the logical thing, and they increase their volumes.
Donald Hitching from Town International. Martin, thanks for the next presentation. Question is, you mentioned Keystone versus open hole,
Yes.
and obviously different areas are proponents of one over the other. In your experience, have you seen advantages of one over the other, and also what impact does that have on refractory?
Okay. So yeah, there are major advantages of one system over another, one approach, if you like, open hole over Keystone. I'd have to say, for the moment, most shale plays, almost 100% of shale plays, are cased cement. The back end is unusual in that it's not really a shale. It has a shale feeding through walls or the back member, but they're plastics. And we've got a lot of big shales that are actually not quite shales anymore. Silty and sands. But if there's a rule of thumb at the moment, it's that shales are typically developed with case cemented for a number of reasons around the stability of the hole as well, and the ability to get the jewellery down into that hole. On on Darcy kind of rock behaviour, if you look at Granite Wash, East Texas Column Valley, that kind of red oak, where you have clastics that are tight and require fracturing to actually produce, I'd say the trend is towards open hole, because you always want the open hole efficiency. If you can run open hole and you can gain that efficiency of dropping the ball rather than having to rig some equipment up and move from one stage to the next, you want to access that. I'll counter with, you do have to understand you've cut yourself off from the z-axis, and you have to accept that. I think the statistics it runs at, again, the number out of the air, and I hate doing this, 15% of the time you're going to get some form of failure. So if you run a number of stages, 10 stages, 15% of those stages are going to fail. The frac is going to be placed where a previous frac has been placed. There's going to be some loss of isolation. Something which you don't get with case perforated, but you do with open hole. Again, it's a very complex question. Again, with open hole, you get all the natural fracture capability, which you don't in case cemented. So if there's any secondary permeability in the system that you're working in, it's another reason that you'd like to move to open hole, is that you have more potential deliverability to the well. So it's moving down from conventionals through tight open hole application. How much it will get all the way into shales will I think come down to how robust the systems can be to deploy properly at the end of the day. Yes, sorry.
John Harris from Bedrock Drilling. Just curious to get a bit more detail on what you sort of see the holy grail to be in terms of the therapy configuration. I know you sort of avoided giving us specifics, but from what you've described, conventional, readily available ECPs in Talent and Arsenal, for example, sliding sleeves, Halliburton, ball drop sliding sleeves, various size seats. They've all been around for a long time. You mentioned then sort of 15% failure rate. I think using that kind of technology, that still strikes me as better than the 1/3 success rate you described in the case dog. What are you trying to get to, I guess, is what I'm trying to...
So some balance, it has to be an economic balance, some net present value engine, that how much of this equipment can I afford to place on the horizontal well to access that benefit of increased density of surface area of access to the reservoir. So yes, there have been some systems around for a number of years. They've only just, I would say, recently started to dramatically increase the number of stages that they can place. There are only just systems available now that have got novel approaches such as one-sized ball or disappearing balls. So another issue around these balls where they were all floating around down there and they were causing havoc with subsequent operations if you had to halt due to a screen in the middle of an operation. But there are disappearing balls now. You can come back to that well and everything's gone. The balls of this nanotechnology material just effectively disintegrates and evaporates. But it all comes down to cost. In North America, it costs more than not going to do it. So you have to get the cost to a place that it's in balance with accessing the resource. I can understand how we got to where we got to because we had a very specific remit which was fast and cheap and actually made it work. I think that now that we've achieved that and there's a lot more innovation available to us, especially during the last 2 years, 18 months, in lower completion technology, but it's time to challenge some of our fundamental assumptions and not automatically think 30,000, 40,000 horsepower is the starting point. Why? And when we know what the problem is downhole, why not go back and think just a little bit differently? And what would all those costs look like? I would hope that there'd be an appealing outcome.
So it's fine-tuning what's currently already, most disappearing balls have been around for a long time, so it's sort of fine-tuning what's already available
And some innovation.
And changing mindset.
Yes. Yes, sorry.
It's Stuart Pankett, Salford University. Talking about 1/3 and hopefully trying to get that economic factor down. But obviously when we're becoming more effective, we're going to be increasing the amount of gas produced and therefore hopefully having an effect on the gas prices. That's what we're trying to sell the general population here to try and get fracking in. So how can we be sure that we're actually going to get to, say, 1 1 in 1 or 1 in 2, which you were saying before? Are we just plucking those figures out? I speak to not only my student, but I used to be a counsellor, and I was desperately trying to get back into the Northwest, and I'm a big supporter of it. And we're up against people that anything you throw at them, they will come back and say it's a lie or it's voodoo science.
So you know, as discussed, we've effectively almost made gas a distressed product in North America. So we're looking for other markets to ship it to try and rebuild some of that business case into it. But if we can, so if you look at most rules of thumb, but most gas plays, and certainly dry gas plays in North America, as Rex Tillerson said just a few weeks ago, everybody is losing their shirt at $4 an MSCF. Everybody. There's nobody making money on dry gas at $4 an MSCF. Now, if we could make twice as much gas out of the same investment in steel and construction for a small increment in cost, and we could probably do it at $3 an MSCF and stay in business, because we're only talking about tweaking what we're already doing in terms of access, financially impacting that a little bit, but doubling the amount of rate and reserves that we're getting off a single location. So that makes it more compelling. But we do have to. I think you'll see North America cycle around, because there's a lot of industries flooding back to the US now because of the cheap input feedstock that they've got for the petrochemical industry. You're also seeing a lot of high power utilization industries starting to come back from overseas because they've got that longevity of access to a cheap energy source. So eventually, and coal-fired power stations, I would hope to see start closing and gas-fired start opening. But they're long wavelength market improvers, if you like. You know, with that, it takes some time to turn a country over to that thought process. And there'll be a new bottom line. It will be $2 or $3 an MSCF. We can't do business when the gas price is lower than this, and we'll have to come up with some other innovation to get more for less in order to achieve that. Yes.
You made a big deal at Aerospace of University. You were talking earlier about fracking being very water intensive, but then you're finished producing a lot of wastewater.
Yes.
Do they normally just re-inject, do a lot of water re-injection in these fracking reservoirs?
So in North America, most flowback water is re-injected, I would say. It's not returned to the cycle, which is why it's seen as consumption. That's why we'd like to start using more of our own flowback water in whatever form we can around well construction to ensure that we're minimising that consumptive aspect. It's of course, when you're in unconventionals, that includes coal and methane, and there's coals, and no better filter in nature than coals. So we produce a lot of fine water from unconventional business in coals.
John Hodnell from Oxford University. Back to your analogy with the glass, and where you applied the kind of isotopic stress regime in the States and how to get dendritic fractures. Based on the Bowman share in Britain, where the quadrillion report suggests there was quite an isotopic stress regime, do you feel that the fracturing here will be successful?
So it's one of the things that we need to look at. Stress state definitely has an impact, because if there's a high stress anisotropy, nature likes planar fracturing. It likes to give you that single plane. If there's something like a rock fabric behavior, so again, coals are a great analogy, where you've got butt cleats and face cleats, and you pump into that system, then there's a tendency for dendritic behavior because of those pathways that open up. But if those pathways are opening up against a higher stress, it's certainly more difficult for nature to provide you with that solution. So if you see a high stress, it's one of the first things I do as an engineer with BP. If we're looking at acreage around, I'm looking for mountain ranges and tectonic behavior. I want to know what the stress state is. I know that in certain permeabilities, it's going to be great to have a high stress anisotropy. In high perm, I want a high stress anisotropy. But in unconventional low perm, unless I see a passive base, and it's certainly disheartening when I know that there's a high stress differential. I realise we're going to have to work a lot harder to try and get that complexity into the fracture, and therefore the surface surface area that will deliver in nanodowsing, low microdowsing, the kind of rates that we need. I think the Bowland, the one saving for the Bowland is probably, it's very thick, if I remember correctly. It's a very, very thick formation.
Well, the formation is very thick, but the
Carriage location might be limited. If it's thick and there's a good net piece of thickness, then of course horizontal wells aren't the way to go. You could do something in the vertical, then the costs are dramatically reduced between verticals and horizontals, so it gives you a different set of economics. But it's one of the things I consider, John, one of a number. Yes. So.
And also, there has been any correlation between production of results and the microseismic events, such that there is a good correlation that is repeatable. Could this help in cost saving in terms of avoiding production logging and generating kind of maybe neural relationship between observed production log and the microseismic events, which could now be used to predict the performance of future activities?
Okay, so probably the best papers to read in that area by Craig Sickler and others and his co-authors. And I would say yes, that there are direct relationships between what's referred to as stimulated reservoir volume, SRV, from microseismic and then post-frac production behavior. So that actuated volume, even though the shear events seems to deliver some information in relationship to productivity. I'll counter with the fact that I know Craig's publishing a paper next year about SRV, a misutilized and misapplied concept. And I think that the industry is moving slightly away from it, but at least he's the one leading us away from it. He's going to publish next February. I haven't seen the paper, I've only read the abstract. So it has been slightly misapplied, SRV. Microseismic is the way that we make those judgments because we have to understand that when we frac unconventionals, when we frac conventionals, the pressure trace, the pressure behavior while pumping was one of our key diagnostics. It was absolutely what told us the fracture geometry looked like. We built our business, if you like, in conventionals around that. When we moved to unconventionals and dendritic, you can imagine how many infinite number of solutions there are to any pressure response you get to a formation when you're truly working in a 3D space. So we no longer have the pressure diagnostic, we no longer have any simulator that accurately models what's going on in the formation with respect to that. Certainly they're in their infancy, if they do exist, in various organizations. So microseismic has been, kind of someone switched the lights out, but they put the sound on. You know, we've kind of lost one sense and gained another. And we're still as an industry trying to determine, again, I'm sure this is what Craig's paper is about, what this change in relationship means and how much can we trust microseismic to be a true reflector of deliverability. Because you see some wells that have no microseismic, wired up, you see no microseismic response whatsoever, and then you get a fantastic well. So there are no shear events. So it probably has an interesting stress state. Should probably look at that. It was all tensile behavior that was going on, so we couldn't hear it, but we probably had planar fracturing, and there was probably some permeability of other problems in some distance from the well. So there are always outliers, and it will be play specific, brittle and ductile specific. Very, very, very complex. But work in progress, and Craig Sickler is really the author to follow. Yes. Sorry.
Within your talk, you draw an analogy in tracking strip mine. I wonder if just a suggestion, if you use that term in this market where fracking is not quite adaptable to the community at the moment. Then use street mining. Issues associated with street mining, subsidies and all that, people begin to think about. Maybe if you do fracking at a compound like this, there's going to be subsidies.
But my first point, just mining is the analogy. But mining from adjacent stopes of material is what we should be saying. But that's really what it's about. There's very, very little Darcy behaviour at this end of the scale. People still try to utilise reservoir simulators to determine what's happening with declines from these wells and productivity, but it's really futile because they are not Darcy behaviour. Yes. Sorry. Next.
Can I just come back to your previous point about microseismics and not being able to get tensile fracture? I'm curious, have you ever seen any cases where you have evidence of from other sources like temperature logging generated of for example, of uncontained fractures where the microseismic has indicated that the fracture probably was contained?
I'm sure those cases exist. There's a new surveillance technique that's gaining applicability, which is distributed temperature survey, distributed acoustic survey as well. So DTS and DAS. And what this is a continuous fibre that's run in a housing from surface and either cemented in or an open hole in most cases. And so we can actually see where the fluid's being distributed at the wellbore, and we can actually listen to the crack at the wellbore as well, listen to the fracturing at the wellbore. And there's a lot more information just within the last 2 years been published on that, on those aspects. But almost undoubtedly there are cases that seismic has demonstrated very good confinement or unconstrained height, and then there have been other diagnostics that say, well, hang on, geometry would suggest that. Yes, sorry.
It strikes me that last month we had one of your distinguished lecturer colleagues speaking, who seems to be putting forward the opposite idea of less stages and more geological evaluation, whatever, to determine where to place those things. And natural fracture seems to be the key thing. So, I mean, if you can comment on that, and also with yourself being with BP and involved in all this, you know, where do you see the industry heading, and are you actually trying to use your concept, smaller frac stages, smaller locations?
Okay. So there is still a lot of uncertainty as to how much conventional petroleum engineering disciplines should be applied to unconventional disciplines. There are very, very successful North American operators that really do everything on the geometric basis. I would love to have them access to the magic log that tells me where I should be fracking and where I shouldn't. I haven't seen anything that convinces me to date. I'm familiar with most of the log capabilities that we have. I haven't seen anything other than if there is some secondary permeability, something in that form could absolutely, because it may represent or provide you with access to much more surface area than you could ever generate from a frac anyway, if it's consistent and widespread and exists over a large area and drains, very much what we try to do in the back end, drains the shale through access in that way. So secondary permeability and true measure of permeability being very, very important. If Darcy plays a role, if you know, there are transient periods associated with this, and you can have interference between fracs, then absolutely less stages is the way to go. But we're not getting interference down at this level. You can see how close these wells are together. Everyone's putting them this close, and we're trying to cover the rock volume between the wells themselves. As for BP, yes, we've started to do certain things in certain different ways. I would say that we haven't. No one's really gone the full extreme to downsize, but it's very appealing to international operators. I think it will be the international market that drives this and takes it back home, because if I want to do something like this in Southeast Asia, I don't want to ship 50,000. I want to do some exploration in shales in Southeast Asia. I don't have to ship 50,000 horsepower down there and have it available on contract. I can use a small amount of horsepower that's available in country. Yeah, they better look at what the well deliverability might be, because you're doing the best job that you probably could, and then determine the economics and the staging. I'm not saying individual staging is it's ideal, but it might not be economic. If 2 clusters with ball drop that pretty much guarantees that you're flipping from one to the other seems like a very good starting point, and we may be clever enough to move to 3. When we start to get to 4 and 5, I think that we're really pushing the edge of our capability from an engineering perspective.
Jeff Cole. You showed us the build up over the last 5 years of use of horsepower. Has that been just amongst the main contractors, or has additional capacity developed?
There are a number of new players in the market, not just the traditional suppliers. That is a summary of most of the majors. It's not got the small outfits that have got maybe 1 frac fleet, 10, 15, 20,000 horsepower. But all of the new players, Canadians and various investment corporations that have started businesses are represented on that list. And there are a lot of them.
Is there a lot of the innovation coming from those newcomers?
I would say yes, to a certain extent, because again, if you look at the majors, they have so much invested in, for example, diesel engines. To offer to convert from diesel to either a dual fuel or all the way to electrification would be a huge piece of business to do. So I think there's more innovation coming from the people who are putting a fleet together, or 2 fleets, from a clean slate basis. So yes, I think the innovation is coming, as it has tended to a certain extent, in the smaller players. It soon gets absorbed into the machine. Yes.
One key factor which we probably haven't discussed tonight, and is a sensitive issue, is well integrity.
Yes.
In the States, obviously, there's been wide discussions, and now the government have stepped in on firmly and made a position very clear. We have yet to reach that position in Europe, and it's still a long way from there. Throw a number out in the air, and when the best fracking will be seen in Europe and UK.
So fracking's been here for a long time, in various forms, but onshore and unconventionals, and we've been fracking coal bed methane in the UK for a long time. When will it come into shales? With a thoughtful approach. One of the difficulties, probably the biggest difficulty, is not going to be what we demonstrate we can do, and the integrity can be managed. If you're pumping at lower pressures, there's a much better chance of retaining integrity longer term anyway. But I would say that the biggest challenge in Europe is that, as Getty said, the meat shall inherit the earth, but not the mineral rights. So in the US, one of the reasons this is very, very successful is most of these people that are affected get a check at the end of every month. They have mineral rights. So there's a lot of federal land, there's a lot of state land, but there's a lot of private land. I don't see that model anywhere in Europe. I guess it's all crown property in the UK, so crown mineral rights. So very, very difficult to see how people will put up with the social impact and not get the check at the end of each month, the royalty check. But I think it will come eventually if the costs pan out, if it can demonstrate that it can be done in such a way that it can be cost effective with other sources of gas, then fine. I'm a little sceptical in that the US had some major tax breaks and had access to an infrastructure, pipeline, rigs, oil field in general. There's still a monstrous number of rigs running in the US. And that whole infrastructure and cost base is not really seen anywhere else in the world. There's very, very few places that have got close to it. Costs will be higher, therefore productivity needs to be higher, or the market rate needs to be higher. All goes hand in hand. I'd like to see it develop. I'd like to retire.
I think we're done. Thank you very much.
Oh, sorry.
In my early days in Shell, we were always told share the cap rock underneath is your fabulous sand, oil bearing or gas bearing, and drill through the shell and produce oil, gas, etc., etc. Now, is it naive of me to assume that now we have the shell or the shell gas, that the gas in the oil has been leaking upwards into the shell, and we've only just discovered it by fracking, or is that incorrect?
Well, in unconventional, I mean, the resources has mostly been, it's often the source rock, it's often the source that's actually filled the reservoir. But yes, it is highly impermeable. There are laminations and KH issues that ensure that it remains a cap rock. I say it's more it's less permeable than the cement that we isolate reservoirs with. But often, the interesting thing about exploration is why you have to be careful when you move from conventional to unconventional. Because people want to go out, prove with well number one that the resource is in place, delineate, and then go head off and set development underway. Don't do that in unconventional. The resource is in place. It's not one of the things that I need to understand. It's almost always there. I need to understand what the deliverability will be after I apply the stimulation solution. So it's a different set of challenges for exploration and appraisal than conventional. It's very odd about that. The quantity and the volume is almost always not in question.
So rather than thinking of the shell as a cap formation for the sand underneath, you're saying it could be the original reservoir.
It might be a source for something somewhere else. A cap rock. It wouldn't be.
It's not correct to say that the gas oil would have been leaking upwards into the shell.
To some extent, but not extensively. There'll be some into the cap, but not extensively. KH and shales is very low. It's a good cap rock. That's why it takes a great deal of work and energy to be put into it to make it into a reservoir.
Okay, well, I think we have one now. Thank you very much.